Right, let me just introduce our guest. Good evening, everyone, and welcome to CAWASA webinar number 12 in our 2024 series. I'm Ignatius Jean, coordinating this out of the CAWASA offices in Lucia. Our guest today will present on operation and maintenance of mechanical, electrical, instrumentation, and process automation systems for drinking water supply. He has some 35 years of experience in technical management of municipal drinking water supply. He retired in April 2024 after working at the largest Dutch drinking water company, Vitens. He was the manager at the production department of Vitens for 30 years. During this period, he was responsible for the operation and maintenance of mechanical, electrical instrumentation, and process automation systems of the drinking water supply of Vitens, with nearly 100 drinking water treatment plants. Through international assignments, he was acquainted with the design and build of drinking water supply systems with local circumstances in Asian, Latin American, and African countries. During these assignments, he acquired experience in optimizing pumping systems by improved design, maintenance, and operation. Over the past 10 years, he has been training local technicians in conducting energy audits at drinking water supply companies in Uganda, Tanzania, Malawi, Colombia, and the Philippines. So this evening, he's going to present the following topics or discuss the following areas: basics of centrifugal pumps and electrical motors, hydraulic power, electrical power and efficiency, how to do an energy audit on a centrifugal pump, procedure, necessary equipment and system data, results of energy audits with practical examples of recommendations to reduce the energy consumption of a centrifugal pump. So without further ado, I introduce you to Mr. Kees Hagen, who was taking time at this hour, witching hour of the night in the Netherlands to be with us in the Caribbean. Thank you, Kees.
Thank you very much for your introduction, Mr. Ignacio. Okay, I will try to share my presentation now. So can you see my presentation now?
Excellent.
Confirm. Okay. I want to tell you something about my experiences with energy audits. On this front page, you see some instruments that are used, and I will discuss them later in the presentation. Mr. Ignacio already introduced me, so I skipped this sheet. And the program for this webinar is basic understanding of centrifugal pumps and pumping systems. I'm going to tell you how to do an energy audit very briefly, because the time I've got for this presentation is really too short to deep dive in this subject, but it will give you an introduction to it. And I will show you a number of results I've gathered in the past 10 years with doing energy audits. Now, why should you do an energy audit? It's presented in this picture on the left side of the sheet. On the sheet, in this circle, you see the total cost of ownership of a centrifugal pump, with this pumping a clean fluid like water. The blue part is the capital cost of buying and installing a pump. The small gray part is the spare part and labor of maintenance of the pump. But the orange part, more than 3/4 of the entire circle, represents the energy costs during the life cycle of a centrifugal pump. So it's really important to try to engineer, select a pump, and maintain and operate the pump to keep this very large orange circle as small as possible. Now we are talking about power, and I want to introduce to you some formulas. Like the hydraulic pump power, you can calculate the hydraulic pump power, the power that is supplied by a centrifugal pump. You can calculate it by measuring the pressure difference over the pump and multiply it by the flow. So that's the first introduction of how you do an energy audit. You are going to measure pressure before and after the pump, and you're going to measure the flow. And then you can make calculations on the hydraulic pump power in kilowatts. To measure the electrical power, we use an instrument like a power analyzer, and it measures the power of a pump, but you can calculate it as well by multiplying the voltage with the current, multiplied by the root of 3, and multiplied by a power factor. So there are 3 factors in this calculation which influence the power, the effective power. That's the voltage, the current, and the power factor. This is really the basic stuff. Now the next step is, what's a centrifugal pump? Centrifugal pump is a rotating equipment which is built to raise pressure in a fluid. And a centrifugal pump has certain characteristics which are shown in this sheet. On the left side, on the top graphs, you see the vertical line, you see the pressure, and on the horizontal line, you see the flow. Now, the most important characteristic curve of a centrifugal pump is the QH curve. It's the relation between pressure and flow. And most centrifugal pumps do have a characteristic like this. You have a certain pressure which is supplied by the pump when the discharge valve is closed, so there's no flow. And when you slowly open this discharge valve, you can see the flow increasing and the pressure decreasing. Another curve, that's the black one, is the efficiency curve. Now you can imagine that when you let the pump run and put energy into this pump, and you close the discharge valve, it results in a very low efficiency. In fact, the efficiency is 0 because you have pressure, but you have no flow. But when you slowly open the discharge valve and the flow is increasing, you can see that for normal centrifugal pumps, the efficiency will increase up to a maximum, but at a certain point, you see this curve decreasing. So when the flow is getting too high, the efficiency is dropping again. On the lower graph, you can also see on the horizontal line the flow, and on the left side the power. Now, the power increases, shaft power of the pump increases with a higher flow. There's also an NPSH curve, but I don't discuss this in this presentation. Now, when you install a pump and you put it in a piping system and you let it run, it will automatically look for a duty point. It will work on a certain point. It's called the duty point on its QH curve. So in this case, on this curve, you can see that it's running at 40 cubic meters per hour at 30 meters of pressure. This duty point is depending on the system curve. The system curve is the relation between flow and pressure of a piping system. So the piping system and the pump are looking for a point on which they work, on which we are working. It's called the duty point. This so far the characteristics of a centrifugal pump. A centrifugal pump is driven by an electromotor, usually an asynchronous electromotor, and this also has some curves. On the left side, on the top diagram, you see the cosinus phi or power factor. That's the light blue line, power factor, which will increase with power. So we have the highest power factor with the full load of an electromotor. So when you are selecting a pump and you select a pump with a too big electromotor, you can expect that it will run on half of its maximum load, and it will result in a lower power factor. And that can cause higher costs from your energy company. The black line, the top line, is the efficiency of the electromotor. Now, as you can see, already at like a 30% of load, the efficiency is getting very high and stays high during the different loads that the pump has. Lower diagram, you see the power of the pump increasing with the load and the speed of the pump, and it slowly decreases with the load because it's an asynchronous motor. That means that there's a certain slip. Now, we are talking about pumps, we are talking about motors, and in a pump motor system, we put energy in, we put electric power, we feed the motor with energy, and there is hydraulic power. You saw the formulas to calculate this hydraulic power, which are supplied by this pump. The supplied power and the hydraulic power are not equal. There are certain losses in this system. We have motor losses because the efficiency of an electromotor is lower than 100%. So the shaft power, that's the power supplied by the motor, is lower than the electric power that you supply to this motor. Now you supply the shaft power to the pump, but the centrifugal pump also has pump losses. It means the efficiency of a centrifugal pump is also lower than 100%. For large pumps, the maximum efficiency of a centrifugal pump can reach like 70-75%. With smaller pumps, like 50-60%. So there are in this system motor losses, pump losses. And you supply hydraulic power, which will move your water, and the water that you supply as a water company to your clients. Now you can also imagine that when you lose water, because when you have leakages in your distribution piping system, in fact, it's also a loss of energy because the water that you lose by leaks has been pumped by this pump, so it has costed electrical power. So energy losses also have a relation with non-revenue water. Now, in the previous sheet, I've explained to you the QH curve. In this sheet, you see the QH curve of a pump, and you see the efficiency curve of the pump. That's the light blue line, and there's a certain maximum efficiency. It's called the best efficiency point at which the duty point of this pump should work. Well, there are always changing situations in which pumps are running, changing suction pressures, changing discharge pressures. So it won't be one duty point on which pump is working, but you always want to try to select a pump which is running in a certain recommended operation zone in which you have maximum efficiency which is possible for this pump. Now, when you do not run a pump within this recommended operating zone, you get effects that will reduce the lifespan of a pump. Because when you run out of the efficiency and you get you ask too much flow of this pump, you can get cavitation, which can reduce the impeller life. But when you run a pump, for instance, with a partly closed discharge valve, the pump will run with a lower flow, so it will run with a low efficiency, but it will also reduce your impeller life. It can give vibration, which can reduce the lifespan of bearings, etc. So it's not only efficiency and the lowest possible energy consumption for running a pump in its recommended operating zone, but it's also very important to have the optimum lifespan of a pump. So to let your pump run in its recommended operating zone. Go to the next sheet. I explained to you the pump curve. I'll also mention the system curve. That's the pressure curve of the system in which the pump is running. And usually we have, when you look at a pumping system, you have a suction reservoir, you have a discharge reservoir or whatever, or a discharge system with a certain static pressure. So it's the pressure difference over the pump already available when the pump is not running. Now, when you start this pump and you let it run and let it transport the water, you also get some dynamic losses in this piping system. So the total head of the pump is addition of static head and dynamic head. When the flow of the pump is increasing, the dynamic losses, the dynamic head, will also increase in a curve like this red one. So at zero flow, you start with the static head. At zero flow, you have this already existing static head over the pump, and when the pump starts running, the flow starts running, the head of the system is increasing until it meets the pump curve, and you have your operating point or your duty point. So when you are designing a system, it's very important to calculate the behavior of your system. So you can calculate your system curve, and when you have calculated your system curve and you know the desired capacity, you can select a pump with a pump curve that will run in its optimum efficiency range. Now we go to the next sheet. There are a lot of existing pump systems that have been designed and built in the past years. And after a certain amount of years, you want to know if such a pump is still running optimum. That's why we do energy audits. Because we already know that water supply is an energy demanding process. Costs of energy are high and rising. A lot of water companies want to contribute to Sustainable Development Goals of the United Nations. So that's a reason to look at your system and to look at how you use your energy and what opportunities you have to reduce your consumption of energy. So proper design, dimensioning, operation and maintenance of water supply systems and pumps is very important to ensure your optimum energy consumption and reduce costs of energy. What we also know is that during its life cycle, these supply systems usually are expanding, changing, clogging, all things are happening in the system. That also can be a reason that a pump that was designed properly is not running optimal anymore. So we do an energy audit, and it's a method to judge a pump and its water supply system on its energy performance. And there are a lot of measures you can take to reduce energy. And some of these potential improvements I will give in this webinar. Now, this was some basic information to start with. Now I want to tell you something about energy audits itself. It's a very brief explanation. If I want to teach you how to do an energy audit, it will take me a few days because there's a lot of practicing to be able to draw proper conclusions. But I will start with what do you need to do an energy audit? You need an energy analyzer to measure the energy that the pump system is using. You need accurate pressure indicators to measure the discharge and suction pressure. You need accurate flow meters. And usually the water is coming from a tank or a borehole, so you also need a level gauge for measuring the water level in the suction side of the system. For doing an energy audit, you want accurate results, so you need electronic equipment. I also always use electronic pressure indicators and mobile ultrasonic flow meters, because my experience is that a lot of mechanical pressure indicators and flow meters are not accurate enough for doing a good energy audit. What you also need for an energy audit is the original pump curve of the pump and the design data of the piping system, so I can do my own calculations of the system and compare them with the measured results from the instruments. It's also important to have is elevations of suction levels and elevations of discharge levels in case of supply of a reservoir. Now, with all this instrument and with all this data, we go into the field and we are going to do our measurements. And all these measurements are gathered in Excel. I've made some Excel formats. So we measure the flow, the mobile flow meter. We measure the discharge pressure. We calculate the total head. We calculate the losses. And with this information, we can calculate the hydraulic power of the system. And we also insert the measured power, the actual power measured by the energy logger. And with these two powers, we can calculate the pump set efficiency. So in this case, this is an example from Malawi, from capital city Lilongwe water supply system. These pumps had an efficiency of about 60%. What I always do, I plot the measured data at different flows, but I also plot the original QH curve, and I compare the measured curve and the original curve. And in this case, you can see that there is a slight difference between the measured curve and the original curve. And you also plot the efficiency curve of this pump, because that can give us an indication of in which efficiency zone the pump is running. So in the end, after measuring and calculating, we get this kind of results. And from these results, from these curves, we can draw conclusions. So we compare the actual efficiency of a pump system with the original QH and efficiency curves. And we can calculate the energy losses and evaluate it. Now, in this example, I show you some of the results from this energy audit in Malawi. We had an actual flow of 160 cubic meters per hour and an actual efficiency of 68%. But the maximum theoretical efficiency for this pump is 75%. It's in this range. We measured about 68. So there's an improvement of 7% possible. The reason for the deviation of this QH curve, because it starts on the original curves, and with the increasing flow, it slowly drops below the original curve, might be internal clogging or wear of the impeller. So in this case, I advised the water company to maintain this pump. But you can also see that this pump is giving more water than what it's designed for, because it's designed to give about 110, 115 cubic meters per hour. So basically, this pump is slightly too big for the system. So this kind of conclusions you can draw when you have done a proper energy audit. Now, after doing energy audits in many countries around the world, I've found several measures to reduce the energy consumption based on the results of the energy audit. You can, for instance, you can replace a pump with a low efficiency by a better designed pump with a higher efficiency. You can replace an electric motor by a motor with a higher efficiency class. I will explain this in my later sheets. You can reduce leakages in pump and distribution system. That also means reduce the non-revenue water. You can check valves, strainers in the system, pipe constructions, etc., which are restricting the flow. You can optimize the power factor of the system, or you can increase pipe diameters of the system to reduce dynamic losses. You can monitor, clean, and maintain the system. This picture on the right side is an example of a clogged pipe, which I found in the system in Malawi. In some cases, you can improve the operation of the pumping system, or you can consider solar energy supply if the conditions are favorable for that. Now in the following sheet, I will explain these measures. In this sheet, you see a recent result of an audit in the Philippines. Blue one is the QH curve, original QH curve of the pump. The green one is the efficiency curve of the pump, and the red one is the power of the pump. Now on the right side here, on the red dot, that's the duty point which was measured during this energy audit. Now, as you can see, it's completely at the right side of the QH curve. So this pump is giving much more water than what it's designed for. This also means that the efficiency of this pump is lower than 40%. But when this pump would be running in its optimum efficiency would be above 60%. Now, I found out the reason for this situation. They originally designed this pump for an older distribution system, and it was running properly, but they decided to enlarge the diameter of the distribution pipe, which resulted in lower dynamic losses, so the total head of this pump decreased, but it also meant that this pump is giving more water. That's what they wanted. They wanted more water. But they weren't aware of the fact that the pump was now running at a very low efficiency situation. So I advised them to select a new pump, and they would be able to increase the efficiency with at least 25% and reduce energy costs. And depending on the size of a pump and other changes that might be needed in the system, the payback time of such an investment of a new pump can be about 3 or 4 years. Another way of reducing energy consumption is replacing an electric motor by a motor with a higher efficiency class. In the past 20 years, suppliers of electromotors have been able to improve the efficiency of electromotors. And industry has introduced energy classes, the EAX class. And the lowest class that you will find in the field is a IE2 class. And the efficiency curve, the relation between efficiency and power of the pump is the red curve. So maximum efficiency of this motor will be about 93% for high powers. The actual IE4 class, that's the class that's available now in the market, will have an efficiency of at least 5% more. So for higher powers. But when you have an electromotor of about 10 kilowatts, there's a difference of about 8 to 9% improved efficiency. So it's really favorable of replacing electromotors because payback time of an investment usually is about 3 to 5 years in reduced energy consumption of the system. Now, I think everybody will recognize this. Reduced leakage in pump and distribution systems, reduce your non-revenue water. A leak in a distribution system always leads to unnecessary energy costs. After all, each liter of water that's leaking has been raised in pressure by the pump. And well, when you have a leak in a pump room, you can easily detect it, but leaks in subterranean pipes are sometimes difficult to find. But by defining distribution systems in measured zones, the location of leaks can be found more easy. If you want more about this subject, you can look at different platforms on the internet. One example is non-revenue water management, a very good website I found on the internet with this subject of finding leaks and improving non-revenue water. What I sometimes find in pumping systems are failing equipments like valves, non-return valves, etc. On the picture on the right side, you see a non-return valve, stem valve, with a damaged valve body. In closed position, this non-return valve will leak, and water will be flowing back. That's also, in fact, a leak of water, and it's also costing energy. So this is an unnecessary energy consumption. So inspection, maintenance, repair program can prevent these kinds of energy losses. Another one is improvement of the power factor of the systems. I have been doing energy audits in Uganda for more than 5 years, and also trained a local team of a Ugandan drinking water company in doing energy audits themselves. And they found out that in some systems they had a very low power factor, like 0.6 or 0.65. But the building construction, electrical building construction in Uganda is in such a way that they get a fine when they have a low power factor. You can see it here in this power bill, electricity bill. You have 30 million Uganda shillings of reactive charge because you have a very low power factor in the system. Based on this finding, we installed a power factor correction system, and now this reactive charge, after installing this power factor bank, the reactive charge is not a fine, but they get a reward of the fact that they have a very good power factor. So in some countries with some energy companies, you can earn money by improving the power factor. So you have to look very carefully to your power bills. Here you see an example, some pictures of this power factor correction system, capacitor bank. In this case, the annual savings of the system in this treatment plant were about 22,000 euros. So the payback time of the system is about 2 years. So in a lot of systems, they are now installing these power banks. Well, already mentioned it in a previous sheet. Sometimes when you do calculations on piping systems, you can conclude that you have very high fluid speeds in this discharge piping. This will result in very high dynamic losses. This, as a result, of high energy consumption as well. Now, by increasing the diameter of a discharge piping or installing a parallel pipe, you can reduce these dynamic losses and reduce the energy consumption. In the next sheet, I give an example with some calculations. So, in this example, we look at a discharge pipe with a length of 1,000 meters, a diameter of DN250, and a flow of 200 cubic meters per hour. The calculated dynamic losses with just a calculation program I use for this is about 25 meters of water. When you have a pump set with a total efficiency of 60%, the pump power, the loss of pump power is 22.7 kilowatts. Now, when you replace this same pipe, this 1,000 meters of pipe by a DN350 with the same flow, you can reduce the dynamic losses with 4 to 4.4 meters. That's a loss of 4 kilowatts. So you can decrease the pump power with 18.7 kilowatts. Now, with the average electricity price of 20 cents per kilowatt, you will save more than 32,000 euros a year. And this pump is running 24 hours a week, 24 hours a day and 7 days a week. So I don't know exactly prices in your area for pipe construction, but payback time of 5 to 7 years might be able. And the lifespan of such a pipe is very long. So you will earn back this investment, certainly. Certainly you will earn back. Now, inspection, cleaning, and maintaining piping systems, pumping systems is very important. Right? Like what I found in Malawi, pipe with a lot of clogging inside. So inspection, auditing your systems and maintaining the systems can also reduce your energy consumption. Another way of reducing energy consumption can be improvement of the operation of the system. What I find in many situations is that pump systems, the flow is controlled by closing a discharge valve or throttling a discharge valve. This will lead to unnecessary energy consumption. And I can show you that with some calculations in the next sheet. I even found in one situation a flow which was controlled by throttling a suction valve. This also leads to unnecessary energy consumption, but it will also lead to cavitation and damage to your pump. So when you want to control flow, when it's necessary to reduce flow in the pumping system, it's better to control it with frequency control or with a smaller pump. Sometimes pumps are started direct online with very high starting currents. This will lead to higher fixed cost because you need a larger electrical system than necessary. And it can also lead to reducing your lifespan of motor and pump. This very abrupt starting system with direct online. So it's better to use star delta starting circuit or to use a soft starter to reduce this high currents. And I also found out that in some situations, running two pumps parallel also leads to higher energy consumption than one pump in the same system can supply enough water to meet water consumption. Now, there are two ways to reduce flow. You can throttle the discharge valve, and you can reduce the flow, but it will lead to an increased pressure. But you can also use a frequency control to reach the same effect. It's shown in this left diagram. On the top, the blue line is the original QH curve of the pump, and the dotted line is the QH curve with a reduced frequency. Now, when you calculate the power of a pump to this duty point with a throttled discharge valve, it will lead to a power consumption of 23.3 kilowatts. But when you set the point, the duty point to the same value with the frequency control, the same pump will use 17.3 kilowatts. That's a difference of 5 kilowatts. So here I show you here 5 kilowatts of extra loss by throttling a valve. So it's better to reduce the flow with the frequency control. What I also seen in my energy audits all over the world is systems where at night too much pump were running. So it's illustrated by this 24-hour energy audit I did in the Philippines. This orange line is the flow of a certain pump in the system. This pump stopped at 9 o'clock. The blue line is the pressure. Now what you see is that after 11 o'clock, pressure is rising in the system because other pumps within the same distribution area kept on running. In the morning at 4:30, they started the pump again, but still pressure was very high. And during daytime, they had a pressure of about 30, 35. And that was enough pressure for supplying water to all of the clients. So my advice was to install a pressure control system. With this pressure control system, reduce more boreholes in this distributed area to save energy. The last sheet I want to show you is consider a solar energy supply. In the picture, you see an example of a solar energy supply for a borehole. with a capacity of about 30 cubic meters per hour, 26 kilowatts. It's installed in northern Uganda, and it works with a hybrid system. So this pump can run with the solar energy supply, but it can also run on grid supply, which means that during daylight, you don't have any energy costs. For this borehole, it will save about 17,000 euros a year, with the average price of electricity in Uganda per kilowatt. Here you see a picture of the inverters of this solar supply system. This is a system installed 3 years ago, 4 years ago. It has two inverters, an inverter for a grid supply and an inverter for solar supply, and an automatic switch. But recently, suppliers can supply you with an integrated hybrid converter. So you only have one converter, which can be supplied with grid supply and solar supply, and it handles both supplies and switches automatically. So it's more simple to install and it's cheaper. But there are also some reasons to not be able to install solar supply. You must have enough sun, you must have enough space. The needed area for a solar supply system is considerable. So in some areas, like I've seen in Philippines, the areas around boreholes are very small. They don't own any land around this area. So in the Philippines, it's very difficult to install solar supply. But in Uganda, usually boreholes have a lot of free area around it. So they are able to install solar systems. So I hope this webinar helped you in understanding the behavior of centrifugal pumps and motors and the consumption of electrical energy. Well, I also hope that with my explanation, you are triggered to start some program of energy management and energy audits. And well, if you need more information about that, you can always try to reach me again, because I can deep dive with you and do some more trainings on actual energy auditing itself. So I want to thank you for your attention. I hope I've been able to keep it within the given time. And of course, maybe you have some questions. So I hope you will be able to share questions with me, and I hope to answer them.
Right. Thank you very much, Kees, for sharing this very informative and very highly technical for our operators. I think they will find, for those who operate some of these systems at the various utilities, I'm sure they may have some useful questions for you. And I know this is particularly important as we deal with non-revenue water issues and looking at efficiencies of our pumps and also maintaining the pressure within the systems. So those of you, I would invite you now for any questions you may have for Kees. I don't see anything in the chat.
Hey, I'll start, Ignatius.
Yes, Kees. Yeah, Kevin, please.
Hi, everyone. Kevin Carter up in Broward County, just north of Miami. Kees, thank you very much. Exceptional presentation. I learned a lot. Ignatius just mentioned non-revenue water. The Caribbean Water and Wastewater Association has a water loss specialist group, which I'm part of. And, one of the things we've been looking at is thinking of water loss, not just as the amount of money and the amount of water, but also a carbon footprint and trying to reduce carbon footprints. Are you seeing this with the overall system? Like not just the distribution system, but when you're doing your audits, are you also starting to see people wanting to understand how the reduction of carbon is happening? And before you answer that, one of the reasons we're looking at that is the potential to bring grant money into the Caribbean to address non-revenue water. But it also looks like, potentially we could look at facilities as well.
Yeah, I've seen a lot of attention for this. For instance, in Colombia, I've been doing energy audits in Colombia, and they are looking at the entire system, and also related to reduce carbon, etc., etc. And they do a program with the International Development Bank. The International Development Bank has made an instruction of how to do an energy audit, and I will send I've a copy of these instructions, and I can send it. I can share it with Mr. Ignacio, so he may be able to share it with you as well. And it's a complete description of how to do energy audits, and I compared it with my own methods, and well, my conclusion is it's about 98% equal. So I was able to do energy audits for the IDB in conformity with this IDB instructions. Yeah, usually I look at distribution systems, but I also look at treatment systems, and also do energy audits on treatment systems, and yeah, also look at efficiency of water treatment systems, because when you do not handle a water treatment system properly, it also can result in water loss and energy loss, because each drop of water lost is a loss of energy.
Great, thank you. I look forward to seeing that. Thanks again for a great presentation.
Enjoyed. Thank you.
Maybe I could just ask a question, Ignatius. I was talking to somebody in Zambia earlier this week, and they were saying that their energy costs have risen in the last couple of years from 14% of total revenues to 44% of total revenues, with no increases in tariffs. So what we have found is that even in North America, they don't tend to do their own audit of the energy consumption. And I know that IDB has promoted at the CWWA conference the ACRA rating that you talked about.
Rating.
But if you're to bring in a consultant like yourself, what is the cost to actually do an energy audit? Because we found in North America the payback time was very minimal, because we were looking at, if we followed recommendations, between a 20 to 30% reduction in energy costs. So just trying to think for the utilities in the Caribbean, what would be the cost, rather than them doing it themselves, which is they're always understaffed and busy. So how much would it cost to have an energy audit done, and what would be the likely payback time?
Oh yeah, I don't have it available ready for now, but what I do know is that I mentioned Uganda. They have one large water company for the entire country, so it's a huge company which is supplying water to more than 200 large cities with hundreds of water supply systems. And I started doing energy audits in Uganda, and this water company, the National Water and Sewage Company in Kampala, their conclusion was, we want to learn it ourselves. And because of their large company, it pays out to train. I've trained three employees, and they're now an energy audit team, and they are auditing all the systems all over the country. So And I don't have the figures, but I know that this team is earning back its costs because the equipment it's a one-time cost. An energy analyzer, it's about 4,000 euros, and the pressure flow meter 3,000 euros, ultrasonic, a good one, and a pressure indicator 500 euros, an electronic one. So that's a one-time cost, say about 10,000 euros. And that's considerable for smaller companies and for Caribbean islands, I can imagine. But for larger companies, it can pay off, and certainly. And hiring me, for instance, for doing energy audits, yeah, but that will be costly with travel, with hotels, with an audit on a distribution pump usually cost me 1 day, of, and in this day I will be doing my measurements. I depend on the data that the water company is giving me about the system. They must have it available. And then I start calculating and drawing my conclusions. So one distribution pumping system will cost 1 day of labor. But it's an indication.
Yeah.
But I'm an experienced one. Someone who is starting will take a week, I think.
Yeah, so I think it's a very short payback time when you
Yeah.
can consider what can be saved in energy costs, which is
Yeah.
usually, along with labor, definitely the largest cost of a utility.
Yeah, certainly, and it's energy costs, but it's also a reduction in carbon deposits. So it's also an environmental element that you can consider. And in some cases, like in some countries, also availability of power is an issue. So when you are able to reduce your energy consumption, it will also help you in less energy problems, energy supply problems. Like in Uganda, they had a lot of energy supply problems, and that was the first trigger for me to introduce solar supply systems, because they had only 8 hours of energy supply a day.
Right, any other questions for Kees? It must be after 11 p.m. at night for him, so.
Yeah, it is. I'm starting to getting sleepy.
So we'd like to thank you very much, Kees, for sharing this very valuable information with us. I think it was quite a bit for some of us to digest all, but the video or the recording of the presentation will certainly be shared with the participants, and they can always use them in preparing for those who are doing examinations or generally for review in assisting them in their various operations in the various utilities. So I'd like again to thank you very much for joining us, all of you. And thank you, Valerie, for making all the arrangements as usual, and wish you a very warm summer up in BC.
Thank you very, thank you very much.
Yeah.
And I want to thank you all for your attention. And well, maybe I will be able to help you in some other ways with some other issues or some other subjects. So I'm available.
Thank you. And do share with us the information you said, and I will share it with the participants. Thank you very much. This was CAWASA Wednesday webinar. And if it's Wednesday, we discuss from A to Z in water at CAWASA with all our operators in the Caribbean region. Thank you very much. Ignacio Jean signing off. Bye.